Hello everyone, my name is Udit Agarwal and today I'll be presenting our work on LLTFI, which is a framework agnostic tool for fault injection in machine learning applications. So one of the major sources of unreliability in modern computing systems are soft errors, which are caused by high energy particles like neutrons and alpha particles striking the hardware. These soft errors can lead to bit flips in the data path and in the computer memory, including registers and latches. And at the software level, they manifest as either software crashes or silent data corruptions, where a process silently produces a wrong output. And just like any other software, machine learning applications are also vulnerable to soft errors. Moreover, nowadays, machine learning is also used in safe critical systems like autonomous driving cars and surgical robots. And soft errors in these safety critical systems can have fatal consequences. For example, as shown in this figure, a soft error caused an autonomous car to miscalculate the steering angle, which might lead to an accident. And this is not just any other hypothetical example. This is based on a real world fault injection experiment carried out in our group. So in this work, we revisit the question on how to evaluate the resilience of machine learning models under the effect of soft errors. So fault injection is a traditional way to evaluate the resilience of an application. And instead of injecting fault directly into the hardware, usually software-based fault injection is preferred primarily because it is time and cost efficient and does not require any specialized fault injection hardware. So among the software level fault injectors for machine learning applications, most of them work on the application level. Moreover, all of them are framework specific. So for example, TensorFlow and TFDM, they both work with TensorFlow, while PyTorch works only with the PyTorch framework, and MindFlow works only with the MindSpore ML framework. So they are all framework specific. A more severe limitation of existing application-based fault injection tools is that they assume that every fault they inject ends up corrupting the output of a tensor operator. So let me further elaborate this point by first explaining the working of these application level fault injectors. So essentially, they work by injecting a fault in the output of a tensor operator. So for example, assume that the matrix on the top right of the screen is the output of a convolution operator, and these application level fault injectors simply add a bit flip fault in one or more elements of the output matrix. So for example, a bit flip fault changes the value of an element in the tensor operator from 3 to 11. Since the application level fault injection tools can only inject faults in the output of a tensor operator, their ability to simulate transient faults is restricted by the high level abstractions of the machine learning framework. In reality, transient faults affect instructions in registers, and they might not always end up corrupting the output of a tensor operator. So to counter these two limitations, in this work, we present LLTFI, which stands for Low Level Tensor Fault Injector. It's a successor of LLFI, which is another popular LLVM-IR based fault injection tool, but for generic C and C++ applications. So LLTFI is framework agnostic. So that is, it is capable of working with multiple machine learning frameworks like TensorFlow and PyTorch. And unlike application-based fault injection tools that inject fault in the output of a tensor operator, with LLTFI, we inject fault directly into the instructions and the registers, and therefore the fault injection is closer to the hardware, but still it is hardware agnostic. So let me first try to clarify the fault model that we considered in this work. So we only consider transient faults, that too in the arithmetic unit of the CPU and in the data path. Moreover, we only considered fault during the inference phase of a neural network and not in the training phase. So here's how LLTFI roughly works. So we first convert the TensorFlow or PyTorch model to the ONNX intermediate representation. So ONNX is a common format for representing machine learning models written in different frameworks. And currently, ONNX supports around 30 machine learning frameworks. And so ML model written in any of those frameworks can be converted to the ONNX format. So the graph on the extreme right shows how the ONNX model typically looks like. Essentially, it's a directed graph which can have cycles, and every node of this graph represents a tensor operator like convolution or ReLU. Moreover, the edges in this graph shows the data flow between tensor operators. Machine learning model written in any of the frameworks supported by ONNX can essentially be lowered down to a simple directed graph like this. In the second step, we load the ONNX model to the LLVM-IR. So LLVM-IR is an intermediate representation available in the widely used LLVM compiler framework. And here's how LLVM-IR looks like. Essentially, it follows a static single assignment format where every variable is assigned only once, and we have primitive instructions like load, fmul, fadd, and store. But still, LLVM-IR itself is hardware agnostic. So because of these properties of LLVM-IR, it becomes a lot easier to analyze and transform it. So finally, at the LLVM-IR level, LLTFI adds code instrumentation to do runtime fault injection to specific registers and instrumentations. So for example, as shown in this figure, LLTFI injects a bit flip fault in the output of the add instruction here, and the injected fault, bit flip fault, might end up corrupting the output of a tensor operator. Like in this case, it corrupted the value of 3 to 10. So the exact details of the instrumentation that LLTFI do can be found in our paper. Furthermore, it is important to note that even though LLTFI works on the LLVM-IR, it can still identify tensor operators like convolution and ReLU, and can carry out targeted fault injection into specific layers of the neural network. So essentially, even though we are doing fault injection at the LLVM-IR level, we are not losing any information about the original ML model. Moreover, we also have tensor operator level fault propagation tracing built into LLTFI. And I'm personally very fond of this feature because, from the tensor operator graph, it is very convenient to understand in which layer does the fault originates or get suppressed, or how the fault propagates between different layers. So the graph on the screen is extracted by LLTFI. And in this graph, the fault is injected in the second layer, and the fault propagates all the way to the last layer by corrupting elements of the intermediate layers, and finally the faults changes the output of the final prediction of the ML model, thus resulting in a silent data corruption. So we can also externally configure LLTFI using a YAML file. So in this YAML file, the user can specify the name of the layer in which he wants to do fault injection, or perhaps the layer number to do fault injection in, or the number of fault injection experiments, or the type of the fault that you want to inject. So we have a very comprehensive list of options that the users can specify without having to change any code details. Now, to evaluate LLTFI, we used 6 benchmarks with 4 different data sets. We also evaluate using NVIDIA's DAVE2 model, which is a regression-based model for predicting steering wheel angles. And all of the benchmarks that we have their TensorFlow variants as well as their PyTorch variants, and we ran our experiments on both these variants. So as our evaluation metric, we use the silent data corruption rate. So SDC rate for classification model is very simple. It is essentially a fraction of the number of misclassifications divided by the number of fault injection experiments. But for regression-based models, where the output of a machine learning model is a continuous variable, we define a threshold, and whenever the deviation from the original output is more than the threshold, we count it as a silent data corruption. So in the first research question, we wanted to understand the difference in the SDC rates reported by LLTFI and TensorFlow. So recall that LLTFI is an IR-based fault injection tool, which injects faults in the instructions registers, while TensorFlow is an application-based fault injection tool, which injects faults only in the output of a tensor operator, right? So to obtain this graph, we injected a single bit flip fault with both these tools, and we record median SDC rate over 1,000 experiment runs. So the graph here shows the SDC rate reported by both the tools, and the SDC rate is on y-axis, and on the x-axis we have all the different benchmarks. The orange bar here corresponds to the SDC rates reported by TensorFlow, and the blue ones corresponds to the SDC rate reported by LLTFI. The error bar here corresponds to the 95% non-parametric confidence intervals. So as you can see that the difference in the SDC rates reported by both the tools is quite a lot. It varies from 1.1 times to 5.5 times in the case of SqueezeNet. To further investigate the reason for this, huge difference in the SDC rates. In our second research question, we delve deeper to understand how the bit flips injected by LLTFI affects the output of a tensor operator. So as we can see from the rightmost column of this table denotes the percentage of the bit flip faults injected by LLTFI that ends up corrupting the output of a tensor operator. So on an average, we found that only 40% of the faults that we inject are causing the output tensor operator to get corrupted. And this sort of proved our initial hypothesis about the overly conservative assumption of application level fault injections, which assumes that all the faults they inject, they corrupts the output of a tensor operator, but in reality, only 40% of the faults do so. And the rest 60% of the fault gets suppressed by multiplication by zero, or gets eliminated by the ReLU or convolution or the Mexpool layer. And finally, as far as the performance overheads of LLTFIs are concerned, so the profiling overhead, which is like just a one-time cost for code instrumentation and stuff, is 54%, while the fault injection overhead, which is like the recurring cost of every fault injection experiment, for LLTFI, it's 68%, and for TensorFi, it's 87%. So LLTFI is still faster than TensorFi. Now, in the remaining 4 minutes of my presentation, I would like to quickly touch upon an interesting case study that we did with selective instruction duplication using LLTFI. So instruction duplication is a well-known technique to boost resilience of software against soft errors, and it has been extensively studied in the context of CPUs, GPUs, embedded systems, high-performance computing, etc. So the fact that LLTFI can do fault injection at the instruction level actually made it possible for us to evaluate the efficacy of instruction duplications in machine learning applications. So in this work, we considered three instruction duplication heuristics. So the first one is operator duplication, which, as its name suggests, we just duplicate the entire operator, like the entire convolution operator or the ReLU operator. And this heuristic has been proposed by prior work. So now that we have instruction level information about all these operators using LLTFI, we try to optimize the operator duplication heuristic, and then we now propose the arithmetic instruction duplication heuristic, where we just duplicate the arithmetic instructions. So for example, the data flow on the left belongs to the convolution operator, and there are 4 instructions that are called in a loop. And to do arithmetic instruction duplication, we just duplicate the arithmetic instructions like fmul and fadd shown in the green. And after duplication, we also add a comparison logic layer, which basically compares the output of original instruction and the duplicated instruction. And after so if the output of both of them is same, then there's no fault. But if they differ, that means now we have to correct the fault, right? So for fault correction, we have so the first heuristic that we considered is the returning the minimum of the 2 values heuristic. So the idea here is that it has been observed by prior work that only large and positive values, corrupted values, they end up causing a silent data corruption. So if we just return the minimum of the 2 values, then essentially we are reducing the probability of SDC. And the second heuristic that we considered is the bitwise AND heuristic. Essentially, it's an optimization over the prior heuristic, because bitwise AND is just a single assembly instruction, and it's a property of bitwise AND that bitwise AND of 2 values is always less than or equal to the minimum of those 2 values. So so we considered these 2 correction heuristics. And finally, the third instruction duplication heuristic that we considered is called arithmetic chain duplication, where we first identify the chain of arithmetic instructions. So by chain of arithmetic instructions, I mean where the output of one arithmetic instruction goes into input of other, and so on and so forth. And then we inject the comparison logic only at the output only at the end of an arithmetic instruction chain. So if you compare it with the prior heuristic, we had to add 2 comparison logic, but in this arithmetic chain duplication, we just add 1 comparison logic. So it reduces the comparison overhead as such. So the objective of this case study is to evaluate the trade-offs between the fault tolerance versus the runtime overheads of instruction duplication. So essentially, what we found is for arithmetic, we found that arithmetic chain duplication with bitwise and heuristic offers the best trade-offs in terms of the SDC rate reduction versus the runtime overhead. And in a nutshell, we found that for networks like LXNet, like there's a huge reduction in the SDC rate, like up to 100%, with only a very modest runtime overhead of 4.43%. So, in this slide, I'm just summarizing the results of instruction duplication case study, but in our paper, you can find more extensive evaluation of it. So essentially, these results suggest that instruction duplication can be an interesting alternative to improve the resilience of machine learning applications. At this point, I would like to recall that this case study of instruction duplication has been made possible only because of an IR level fault injection tool like LLTFI. So now I would like to summarize this work. So in this work, we proposed LLTFI, which is a LLVM-based IR level fault injection tool. It is accurate and faster than TensorFlow. And the most important thing is that it is framework agnostic. So it can work with machine learning models from a lot of different frameworks. And we also provide an efficient form of debugging in the form of fault propagation tracing. So since the acceptance of this work, we have been quite extensively working on improving the usability and testing LLTFI. And I'm now happy to share that LLTFI now works with some very large NLP models like BERT and GPT. And with that, I would like to conclude my presentation, and I'm ready to take any dangling questions that you have. Thank you.